Good afternoon, everybody, and welcome to our astronomy seminar from the University of São Paulo. And today we have Dr. Benito Marcote from the Joint Institute for VLBI, ERIC, or JIVE, presenting his work entitled Localizing Fast Radio Bursts and Unveiling Their Extreme Environments. First of all, thank you, Benito, for accepting our invitation. And just to tell you a little about Dr. Benito, he did his PhD in 2015 in the University of Barcelona in Spain, working on high-energy galactic binary systems via radio observations. After that, he moved to JIVE, where he's still working today, as a support scientist of the European VLBI network. He also got involved on studies of other transient events from GRBs and gravitational waves to FRBs, which is one of his main projects right now. So before we start, I'll ask everyone except the speaker to turn off their cameras and microphones in order to avoid interruptions. And all the questions will be addressed to Benito at the end of the presentation. And if you're watching this from YouTube, you can write your comments and questions in the chat, and I'll read them to Benito also at the end of his presentation. So thank you very much. Please, Benito, you can start now.
Okay, thank you very much, Mirza. So first, thanks for the invitation to give this seminar. I'm glad to at least reach you through online chat from here. It will be a pleasure to go there at some point, but at least this is a good opportunity to at least connect from the two sides of the Atlantic. So as Marisa mentioned, I'm Benito Marcote. I'm typically, recently worked during the last years on fast radio bursts, which is a relatively quite recent field in astrophysics. So this is a field where there is a lot of improvement, new results, challenging questions that happens every few months actually. So in this talk, I plan to do kind of a summary of the whole field of fast radio bursts so everyone can be more familiar on these sources. And then I will also discuss our work and what we've been doing and what's the status of the state of the art of this field during the last years and where we are right now. So having said that, the first part of the talk will be just a broad introduction on the topic. The most important fact is to make clear what is a fast radio burst or what we call a fast radio burst, and then get to know what's the properties of these events that we can observe. And obviously, one of the main questions that everyone can have is like why we actually care about these sources, a part of more knowledge, but why they have a particular interest for many fields of the astrophysics nowadays. Then once we have a clear picture on what is a fast radio burst, I will go to the second part, which is why we actually are focused on precisely localizing these events in the sky to try to get a good astrometry, being able to associate them to other counterparts, and what we can obtain from there. So this has been proven to be quite relevant in the last years, and this is our current research studies. This is our focus in the last years, and this is basically what we've been spending most of our time. And for that, actually, we are in a project, in a collaboration called AstroFlash, which is based with people in the University of Amsterdam, JIVE, and also Sweden. And within there, we have observations running through the PRECISE project, which is trying to use unofficially many antennas all over the world that belongs to the European VLBI network. So we can actually get a lot of time to be able to trace back this emission in the sky. And the last part is the really recent results that we are getting and how these are placed in the context of fast Fourier bursts. So first of all, we need to be clear what we call a fast Fourier burst. This figure basically summarizes what is this kind of burst. It's a really brief signal that only lasts for a few milliseconds in time, and is completely isolated. We see a flash of light that lasts 1 millisecond, and there is nothing else. And this is a quite remarkable differences with other kind of transient events. Like there is no afterglows, there is nothing either before or after these flashes. And typically they are completely isolated. In most of Fourier bursts, we only see one flash and absolutely nothing after that. So the definition of these events is quite clear. We call them fast Fourier bursts, fast because it lasts only a few milliseconds, even less than that. So far, we've only observed them at radio frequencies, roughly around 1 gigahertz. And this is a combination both like observational biases, because we have most of our surveys centered at 1 gigahertz, but also looks like most of these sources peak, the emission peaks at these frequencies. So far, we don't know if there's emission outside the radio wavelength. There are some models predicting it, but so far we've only detected at these frequencies. And it's a burst that typically is quite bright. It can be easily detected with any radio telescope on Earth. And as I mentioned before, this is a really young field. So the first fast Fourier burst that was ever detected only happened in 2007 by analyzing archival data from one radio telescope in Australia, PARCS. But that means that the field is only 15 years young. So compared to almost any field in astrophysics, this is really young. And that's why any discovery makes quite a huge impact here. And so far, during all these years, we've already detected hundreds, thousands of them. So we've already detected a lot of fast Fourier bursts. However, even if we have a quite large number of events, still the origin is a bit unclear. We still don't have a complete image on the processes that produces these bursts or where they are produced. What we do know is that there are a lot of them. So the rates, and these are estimations derived from the current observational time and detections that we have, is that we basically could detect with the current sensitivities around thousands, 10,000 of fast Fourier bursts per sky and per day. And this is quite surprising because this is much higher rates than what we know for other transient events as supernovae, GRBs, binary mergers, compact binary mergers. So these rates do not match all the other known explosive events in the universe. So of course, this didn't help to explain what produces this burst, but what we do know, and this was the first surprising result that we had, is what we can derive from this burst. So before I only saw a figure with the burst as a function of time, but actually in any radio observation, we have two axes, the frequency and time, because we are observing at different frequencies within a bandwidth. And what is clear in any of these bursts is that the arrival time of the burst is quite different for different frequencies. You see here real data, so the bright line is the burst, and you see that at lower frequencies, the burst arrives at later times. And this whole picture is around hundreds of milliseconds. So while the burst lasts only for a few milliseconds, or even less, the tail lasts for several hundreds of milliseconds, even 1 second, for the usual bandwidth that we have at radio observations. And this is just the effect of dispersion of the light. So we know that the space is not completely empty, and that produces that all the free electrons of the material that are in the space produces a dispersion of the light. If you have the normal emission from most of the objects, you do not see this effect. But if you are dealing with millisecond duration bursts, then you do see this effect. And what is interesting from here or useful is that this dispersion is just proportional to all the material that the light crossed and went through. So from the emitter to the Earth. And what happened here is that this tail, basically, if you have more material, the tail will be longer. The problem is that we do know with quite high precision all the material that are in our galaxy through the different lines of sight. So if one compute the expected delay from the top to the bottom part of the band for the material that we know in our galaxy in that direction in the sky, we will expect a significantly shorter delay. So that means that the material that this bird crossed is way higher than all the material that we know from our galaxy in that direction. So the only reasonable, especially for all the FRBs that we know now, is that these are really extragalactic events, and actually they are not in the local universe. They are really far. So that's the only way. We have a lot of material, which is the intergalactic medium. And this is what is creating most of this dispersion. So considering this, one can use it as an estimation of the distance to most of the FRBs. And this is something that we can do for all the detected FRBs, even if we don't know exactly from which position in the sky or with high precision they came from. And what we detected is that for most of them, we have redshift of around 0.1 to even 2, 3. So they are really far away. So we have an event that is relatively bright, resembles to the emission that we see actually from galactic pulsars, with the difference that these bursts do not repeat. So a pulsar is a completely perfect clock. You have a pulsar in the same time, a pulse in the same durations, but it repeats completely. In this case, you only see one burst. But these are not galactic events. So if you place the same brightness, the same flux that you detect at redshift of 0.1 to 3, means that these events are way brighter than any single pulsar that we know in our galaxy. And this was the problem with fast Fourier bursts. There was no way to explain these luminosities. So to make it clear, this is basically the transient space plot, where we see on the x-axis is the different time scales of different emissions. So on the ranges of milliseconds, on the scales of millisecond duration, we have the pulsars that we know for decades already in our galaxy. Even shorter emission, we know basically only one source, the Crab pulsar, that can emit even nanosecond emission. Sporadically from time to time. It's something that is not repetitive. But if we place the expected luminosities for fast Fourier bursts, we see a gap here between the normal pulsars and the fast Fourier bursts. And if you focus on the y-axis, which is the luminosity, you see that this gap is actually 10 orders of magnitude. So we are not talking about something that is just a bit brighter than regular pulsars. We are talking about 10 orders of magnitude. And there is no way to explain this emission with the same processes, the same sources that we know in our galaxy. And this was the problem that we had with FRBs for most of these years. It was a problem, we couldn't explain it, but on the other way, there were a lot of hypotheses, and then the number of possible scenarios started to grow up during the first years. So of course there were a lot of scenarios, both galactic, extragalactic. Maybe we have something really compact even in our galaxy. You could explain the observed dispersion, but all these models went down, especially after the first 5 years. But again, people try to explain these events coming from known sources. And the problem with fast Fourier bursts, especially until 2019, 2020, is that for most of the times, we always had a way larger number of theories, possible theories, than FRBs ever discovered. So in general, we always had several theories that could fit each particular known fast reverse. But again, sorry, there was a lot of interest during these years to explain FRBs and even to study them. And this is not only because we have something that we don't know and it's really bright. There were other implications that actually make this topic really special interest in different fields, not only radio astronomy or astrophysics. So of course, the first one is trying to explain these single pulses that are 10 orders of magnitude than all the other pulses that we knew up to date. Also because it could have some connection with other parts of the electromagnetic spectrum. We know that there are theories that could predict same kind of emission and counterparts at higher energies, like optical X-rays, even gamma rays. But the importance of fast zero bursts of this field is the following points. Like they have really strong implications on larger scales in the universe. And we need to think that here we are tracing an emission that lasts only for 1 millisecond and comes from a redshift of 1 or even a bit larger than that. And that means that there, as happens with the dispersion, we are actually getting a lot of information about all the material that this light travels through. So actually by studying, and this is just when we go through statistical studies, once we will have a much larger number of fast reverse than now, we have FRBs from all the directions in the sky, we will be able to trace, even with a much higher precision, all the properties of intergalactic medium and the galactic halos from both our galaxy and the host galaxies from this fast reverse. And then they have really critical implications on the reionization history of the universe, how to constrain the baryon content of the universe, that this is something that can be actually proved and constrained with a much better precision due to this burst, and also getting even more deeper constraints on fundamental physics, like equivalent presence and photon mass, because here we are just detecting a burst that travel gigaparsecs, and we are just measuring delays in time of milliseconds. So that means that we are actually putting a lot of strong constraints on the limits for the photon mass and the equivalence principle. Sorry. So this is why we were focused and interested on fast reverse. The second point that my presentation here will have is why we do care about localizing them with a high precision in the sky. Why we really want precise localization of fast reverse. And this is something that has been in the field since the very beginning. So you don't know from where a fast reverse will come from or when you will detect one of these events. You cannot predict them. So, and most of the detections, most of the discoveries have been performed with single dish telescopes because they have a really big field of view. So you can monitor a larger field of the sky at a given time and getting more time on that. The problem with that is that your resolution is really poor. We are talking here around R minutes. So if you only have an a priori position of this burst on R minutes and you don't have any afterglow, any other persistent emission that comes either before or after, there is no way to be able to associate this burst to any possible counterpart. Because in a few R minutes area, you have 100,000 of possible counterparts. So it was clear that we needed to go to a much higher resolution instruments at radio wavelengths, as it's the only ones where you detected fast reverse, means that you need interferometric observations. So either the VLA, and here you see as comparison what is the resolution that you will achieve from VLA or single dish telescopes as Arecibo or Parkes, then you will be able to associate them. But this was not easy because, of course, your field of view is always way more limited. So actually it took 10 years until we finally localized the first fast Fourier burst with enough precision. And this actually happened on the first FRB known to repeat, to show multiple bursts. It didn't have any periodic emission, but we knew that there were multiple bursts coming from this direction at some point, at completely random times. And actually, it has been the first one and the only one discovered by the Arecibo telescope that right now is unfortunately decommissioned, as most of you probably know. But this was actually a fast reverse discovered by this telescope. We know, as I will explain later, that this comes from a really extreme environment. And even if I mentioned that there is no periodicity on the bursts, we know that there are some active periods. In this one, another FRBs. So there are some periods of time where you are more likely to detect bursts, even if these ones don't follow any periodicity at all. The reason for this one is still completely unclear in all the FRBs, actually. But in any case, we knew that this FRB was showing multiple bursts. So what we did is keeping two arrays, the VLA in the US and the European VLBI network that combines telescopes from Europe, Asia, and Africa, and also from Puerto Rico when we had Arecibo. And we kept observing this field in the sky for a long time. We didn't know when we could get any new burst from the source, but that was the motivation and how the only way to be able to localize it. So after a long time, we actually get, and this was the first high resolution image of a fast burst. And this is actually an image that takes only 5 milliseconds of data. And this was a huge improvement or impact in how you deal with radio data, because a typical radio observation integrates hours of data to be able to have a reliable image. So this was not that straightforward. However, the importance of this is that we could basically increase by 2-3 orders of magnitude the resolution, and then we could localize it to their second level with the VLA. And what we found is that actually it was consistent with an optical and radio counterpart that belonged to a galaxy, a dwarf galaxy, of basically 1 gigaparsec. And as I had mentioned before, and is the bottom line plot, we detected actually different bursts, which are represented by the red triangles, and the black circles represent the luminosity of this persistent radio emission. So it was clear that we could confirm that there is no afterglows associated with the burst. The burst seems to be completely unrelated to this persistent emission. So of course, we are talking about a galaxy at 1 gigaparsec. You see a point like optical and radio emission. There is no way with this resolution that you can certify that this persistent radio emission is associated with the burst, because in a galaxy you have a lot of objects. It has an extension. It can be from the core. It can be an putative AGN, or can be some particular compact sources in a different part of the galaxy. So here was the first motivation when we realized that having really high resolution images is critical for this burst. So fortunately, we were observing with the European VLBI network, the EVN, and we actually also detected several bursts. So what we can see here in the left is in contours at color scale is the persistent radio emission. We then realized that this is a really compact source. It's only 0.7 parsecs in size. So it's already more compact than most of the pulsar with nebulae supernova that we know in our galaxy. And more importantly, we saw that the bursts, which are represented here by the crosses, they were consistent in position with this source. And we could trace a upper separation of 40 parsecs. So we know that they are within 40 parsecs in this particular galaxy, which was a low metallicity dwarf galaxy, with an incredibly star-forming region, as you can see on the right, which is the black part. This is optical image from Hubble. And we saw that the bursts actually are coming from inside this star-forming region. And this was really relevant because these particular environments, low metallicity, dwarf galaxies with prominent star-forming regions, are the characteristic hosts of hydrogen-poor superluminous supernovae and long GRBs. So this was the first evidence that maybe these fast radio bursts are related somehow with long GRBs or superluminous supernovae, because at least the host was similar. Also, with this information, actually, we could constrain that this must be a really young source of around 100 years old. So we are not talking about young on astrophysical time scales. We are talking young on basically human time scales, only decades of 100 years old. Additionally, with that, also with the Arecibo telescope, we saw that the environment is really extreme. So first, this emission is completely, fully linearly polarized. We only see one polarization. But additionally to that, we got a crazily high rotation measure. So rotation measure is how fast the polarization of the light rotates with time. And this is basically for the contact. You really need a really high plasma density near to the emission. And values like the ones that we observe here of up to 10 to 5 radians per square meter has only been detected to date in one particular location, in all the pulsars of Magnetos that are really close to Sagittarius A star, the nucleus of our galaxy. So this is a plot with the rotation measure and different dispersions. You see the fast reverse on the top, 121102, and all the dots and red dots are pulsars, the known pulsars in our galaxy. So the only ones that reach is almost the same rotation measure were the ones that are actually next to Sagittarius A star. So basically next to a massive black hole. And actually these are still today the two possible explanations that we mention for this source. Either we have possibly a magnetar that is next to a superluminous supernovae because the host is similar, or we have something similar but interacting with a massive black hole equivalent to Sagittarius A star, plus other interpretations as always. But this reaches the motivation that we really need these very precise localizations to be able to mention this. And again, this was only the first fast reverse that was localized. Later on, a few years later, we localized the second one, also a repeating one, and the environment was completely different. In this case, we detected a spiral galaxy similar to the Milky Way, and it was just next to a star-forming region, in this case similar to solar metallicity star-forming region, but it was right outside this region. So what do you have next to a star-forming region, but right on the edge? It can be some runaway object, like for example, typically you have high mass extra binaries, or other OB associations that they are really born just some kilo years, thousands of years, and then due to the supernova explosion, they are just running away from the star-forming region. But in this case, the time scales of this object is larger than in the first case. So this was the two first localized fast bursts, and both of them had different contexts, different environments. During these years, we got so many localizations, most of them on the arc-second level, so you can only associate them to a host galaxy, but not within that galaxy. Only in a few cases, we will be able to do that. And then we saw that in a few cases, they are also related with star-forming regions, but not in all of them. So still, the idea that we have something similar to magnetars because they can produce this kind of emission in a very young object was still around. And one huge discovery was an FRB-like emission not entirely like a fast-Fourier burst, but similar, that came from a galactic magnetar, a known galactic magnetar. So in this case, this galactic, so the flux that we observed was crazy. It was kilojansky, megajansky per millisecond, and it was coming from an actual magnetar that we knew. And even more importantly, these bursts were associated with X-ray bursts, basically certifying some of the models that were predicting that these kind of events must come from the magnetosphere of a magnetar, a young magnetar that still have enough rotation power to be able to emit at these energies. And importantly, with this, we confirm that they may be a X-ray emission, at least, associated with the fast-Fourier bursts. So again, looking for fast-Fourier bursts is really time-consuming because you don't know when they will be produced. So basically, you need all your antennas keep observing in the sky. And until now, we just focus on having very high localization. That's why we were using the European VLBI network during these years. And that's why we reached milliseconds resolution. Right now, we continue observing fast-Fourier bursts with this facility. But of course, the amount of observing time that we can obtain is limited. We cannot get as much as we would always want. Fortunately, most of these antennas that are 25, 30 meters in diameter have quite a spare time, not within the network, just when they observe for themselves. So actually, we managed to arrange an official sub-network of the EVN where we can actually synchronize different antennas and we can get all the free time that these antennas have. And this is how the Precise project was born. So we are basically getting a green time on the antennas up to request and when they are available, sometimes more, sometimes less. So with this, actually, we've reached 100,000 hours during the last 2-3 years. Of course, it requires a lot of effort from both parts. Like for us, we need to organize and synchronize all the antennas. It requires to be in contact with the operations and the antennas, being able to do the schedules, and also trying to synchronize the times where they are available or they can observe, and how to get the data and trying to search for it. So we don't saturate all the local space in all the antennas. So we spent basically 2 years without no detections at all. But fortunately, 2021 was quite a lucky year for us in this sense. And we started detecting a lot of bursts from different FRBs suddenly. Basically in the same month, couple of months, we actually detected 3 different fast-Fourier bursts, while in the previous 2 years, we detect nothing. So one of the first important results that we obtained, it was this fast-Fourier burst, 2011-24A, that it was proven to be really active at the beginning of 2021. So active that actually a lot of facilities started observing it, and actually they got already some localizations on the order of the R-second level. So the GMERT in India, the VLA in US, ASCAP in Australia, and FAST, the 500-meter telescope in China. But all of them had resolutions of R-seconds. And basically that's the size of the galaxy at that distance. So you cannot be able to say where within that host galaxy the bursts are coming from. Well, when we observe with the EVN, actually we detect some bursts. That is what you can see on the left. And our precision is on the order of the millisecond. So we actually go deeper by 3 orders of magnitude. And this was quite also important because it was associated with a persistent radio emission. That was only the second case, because I've been talking about the first fast-Fourier burst that was localized, the persistent emission there that was really compact. That hasn't happened again. There was only a second case recently in the last months that is associated with a persistent radio emission. But for all the other FRBs that we know so far, there is no persistent emission associated to it. Why? Probably because they are all their sources, so that photoactive emission may have decayed. But we are still not sure how to explain that part otherwise. And in this case, we saw that it's actually an extended emission, and it's now confirmed related with star-forming region. So actually, we have another fast reverse related with star-forming regions on their galaxies. So we had a relatively quite clear picture here, where we got relatively young objects, magnetars, probably in very extreme environments, either because of the supernova remnant around it, because we are talking about 10, 100 years old events, or maybe related with massive black holes. So we already have the extreme environment because of the massive black hole. However, this changed recently in the last half a year, 1 year, when we detected this fast reverse. So 2020 or 120 was also discovered by the China telescope in Canada. That has been the facility that has been discovering most of the fast reverse. However, they don't have enough resolution to be able to trace and associate this burst with other counterparts. The interesting part of this source is that it was really next to M81, the galaxy that is actually a measured object. It's really bright in the sky. You can see it on the left, basically, and it's huge. So this was in that area of the sky. And the dispersion that they observed in the burst, it was kind of consistent with being related to this complex there. So we spent a lot of time at the beginning of 2021 observing this area. And in February, March, and then later in April, we actually detected different bursts. And this fast reverse came with two really great surprises, unexpected and really important implications. One is how narrow fast reverse can be, how fast they can emit. So here you have 4 different examples of these bursts. You see that the shapes in time, they are completely different. But in one of them, V3, which is the bottom left part, you see that they are quite a strong and narrow spike. So how narrow is this spike in time? We actually need to reprocess the whole data, even doing upgrades in the correlator software that we used. But actually, we could confirm that this burst had structures on the scales of 60 nanoseconds. So if we mentioned that a millisecond is quite a fast emission, now we went down to just 60 nanoseconds, coming from a few megaparsec away, actually. So actually, this had the important implication that the only emission that we know so far on the nanosecond scales are the crab nanoshots, that we know that they're coming from a relatively young pulsar. And this is actually how this diagram ended up. So I mentioned before the gap between fast reverse and known pulsars. In dark purple, I would say, yeah, is the magnetar, the galactic magnetar that exhibit some FRB-like emission. And now in black, we see this FRB. So again, it was coming from M81 area. So we know with high precision the luminosity, and actually did have the 2 implications. First is an FRB that is kind of connecting both sides. It's a really low luminosity fast reverse, but it's relatively really high luminosity for a regular pulsar. And on the x-axis, we actually went down to the nanosecond time scale. So actually it's really close to the crab nanoshots. So this can be the missing link between FRBs, known pulsar magnetars in our galaxy, and exhibiting the same kind of type of emission. So it has emission on the millisecond scales and also has an emission on nanosecond scales that doesn't happen all the times. But the second important discovery that we reached here is where it's localized. So these are the images that we could obtain for the individual bursts, which is the top row. They were not that nice. But when we combine different images, and we ended up with the bottom right image, we could trace with a high precision on the millisecond scale the position of these bursts. And here the white circle represents one of the globular clusters that are associated with M81. Actually, we go to the optical emission. This is the bright spot, the black one, the white one on the left, or the color scale on the right. And this is a globular cluster associated with M81. So basically, we had a phase reverse in a global cluster, which is the completely the extreme opposite side to any really young star-forming region. Global clusters are known to be the oldest systems in. Still explain this. One is to have a young magnetar, but instead of the normal channels of production, it may have been formed by just pure core collapse. It cannot be formed by core collapse, but it can be created just by accretion or a merger-induced collapse. So this is something that has been speculated to be present in global clusters, although never completely confirmed. Or the other way is to have a low mass X-ray binaries that we know that they are quite populating global clusters. And in that case, we are not talking about a really young system, but something that may be regenerating. So these are the conclusions from this latest phase reverse that basically changed the whole picture that we were building during the last years. This is still the closest extragalactic phase reverse that we've localized up to date. It's just a few megaparsecs away. And as opposed to almost all the other ones that were localized, this is in a very old location. It's in a global cluster. So still we have kind of two possibilities that could explain it. But again, these models do not apply to the other FRBs that were detected so far. So what we are thinking is that maybe actually you can produce bursts from different objects. You just need some determined conditions where these bursts are able to be produced. And the important part that this may be a missing link between galactic known sources and phase reverse. And of course, it confirms again that we really need this precision on the localizations to be able to understand the environments where phase reverse are localized. So these are just the take messages from my talk. Phase reverse are still quite remarkable type of astrophysical objects that we don't have a clear picture of what they produces them, but still it's a really young, highly evolving field. And the important part is that it will have a lot of implications in different fields, as we've already seen in the last years, actually. We already know thousands, and actually the predictions are that we will have a huge number of phase reverse detected, at least, during the coming years. Still, we know that only a fraction of them repeat, and we still don't know why. This is one of the key questions that remains there. And what we've seen here, even in the last one, is that still every time we have a new localization, instead of closing the questions, the open questions that are to date, they start opening even new ones. So hopefully we will have even more in the coming years. And that's all. Thanks for listening.
Thank you very much, Benito. It was an amazing presentation. I'll open for questions now. We have Maria first.
Okay. Thank you very much, Benito, for this great talk on this, for me, fascinating topic. All the information all the new information seems even more puzzling, so makes this extremely interesting. So I am guessing if you can. No, I will ask first another thing. Can you comment on the efforts on the X-ray community to help with this mystery? Are there any? I guess they are at X-rays especially.
Yes, that's actually a good point that I didn't reach. Yes, there are a lot of efforts, not only in the X-rays, especially I would say X-rays, Fermi, and also TV. Because again, as happens in other transient or other type of emission, you typically have a link between the low radio frequencies and high energy, because at the end it's the same population of electrons or hadrons emitting it. The main problem that we have so far, and this is kind of the FRB where you can actually start placing some meaningful limits, is that they are really far. So they are far away, and then you have XMM or Fermi or the GeV range. They are not sensitive enough still. Like we did a few campaigns actually on the first FRB and in other ones, but they still, even in the most promising models, let's say that, because we don't have anything that really predicts something with total confidence. The obtained upper limits on possible burst emission on X-rays are orders of magnitude away.
I see.
And that's something that was demonstrated with the galactic magnetar. Like we would expect probably X-ray emission, but if we extrapolate that luminosity to something on gigaparsec scales, then we are still a few orders of magnitude away in sensitivity.
Okay.
So for cases like this one, the latest one that is only a few megaparsec, this is getting close. And actually we have some campaigns more with the MAGIC telescopes in the TV range. And I'm aware that there are more efforts with Fermi, Agile, and also X-rays. Because in this case, we are getting close to getting meaningful upper limits there. Or of course, if you detect a burst, would be ideal.
Yes.
So there are some campaigns, but the main problem until now is that they are really far away.
I understand.
Plus, you are trying to detect something on the millisecond scales. So you are always need to try to play with the noise that is much higher than when you are able to integrate.
Exactly, and it depends where you detect the burst.
Yeah.
Okay, I will ask another question if I am allowed. I was wondering, what about the statistics? If these objects are magnetars, what the statistics says? Like, is this probable? Of course, from the known population, or this is limited because we don't really know what's the mechanism behind.
That's one of the problems. Like, we are still not completely convinced on the mechanisms that may produce it. So, as many theoretical people say, it's really easy to produce radio bursts because, relatively speaking, to other events, they require just little energy. I mean, we are still talking about a relatively bright event, of course, but we are in the radio regime. The energy, the total budget that you need to produce them is not that high. So it's relatively easy from the theoretical side to at least argue how you can produce those ones. And that's why you actually have a huge number of different models.
Yeah.
So that's one thing that depends. If you talk only about magnetars and then you force them to be only 100,000 years old, then probably you start getting some really deep constraints there compared to all the FRBs that has been detected. The freedom there is that we don't know for how long this kind of emissions will last. Like if you can still get like the ones that don't repeat, so you only see a sporadic burst, maybe they are way older. And that's why actually naturally explains why you only see one burst on human time scales, for example. So you still have a huge range to play. That's the problem. For now, we cannot constrain in any of the directions. So it's hard to say if it doesn't fit the known population of magnetars or pulsars in other galaxies to the statistics that we see in fast zero bursts.
I see. Okay.
But one of the actually ways that is considered right now is once we have enough statistics to trace the evolution, the history of the universe. If the statistics of fast zero bursts in distance follows the star forming history of the universe, it follows other trends there, like GRBs. In that case, you can do it indirectly. That's probably the most feasible way right now.
Okay, so the idea is just to wait to get more statistics, actually, more events.
And we are already next to it, not that far, let's say.
Ah, that's great. Okay, so let's wait for more more observations. Thank you very much.
Thanks for listening.
And now, Professor Elizabeth, please.
Oh, hi. Thanks a lot for the review talk. And I have 3 questions, if I may. First of all, do you have statistics enough to infer that the distribution is isotropic, therefore suggesting a cosmological origin, in the sense that, okay, you may have this a few localized events, but most of them come from very large distance? Because in the beginning you mentioned this redshift range, right? So,
yeah.
Can you comment on this?
Yeah, so indeed, they are from the sky, they are completely isotropic. And this was already seen with the first, I don't know, about 50, 100 events. It was quite clear, or getting clear, that it was isotropic. There is no trend that follows our galaxy. Right now, there is an observational bias, which is the CHIME telescope in Canada, because they are responsible of, I don't know, 90% of all the FRBs discovered. And it's an observatory that you cannot point. So it's always focused on the same part of the sky, and it's in Canada. So it's really way north in the sky. So if you see the map of the position of fast reverse, of course, it has a shift towards the North Pole because of this instrument only. But if you remove this bias, actually, they are completely isotropic. Right, so that also claims about the cosmological origin of all the bursts.
Right. So my second question regards what you said about the fact that they simply not they seem not to repeat, but on the other hand, you have found out some events that are actually repeating, right? So the apparent lack of repetition of, let's say, most of the events, my question is very naive in this way, right? Because could it be this lack of repetition, could it be due to the fact that these are actually events coming from runaway objects, compact objects, as you said, for instance, a neutron star or a supernova explosion or something, a runaway object, so that it's kicked outside of the region. And then when it repeats the event again, it will appear in a different region of the sky, but it's still from the same object. Is that possible? Because you actually cannot localize those events. You said that the resolution is very poor, arc minutes, right? So could this be possible that several of these events are actually events from a single object? That
okay, I will answer first the second part and actually going to the first part of your question. So we can distinguish different FRBs basically because of the dispersion of the light. So as I mentioned before, the dispersion measure, the tail that you see basically in the emission, it's completely proportional to the distance, so yeah, proportional to the distance. And then we see completely different dispersions for different FRBs. And actually, this is the way to classify them. So for instruments that detect a lot of them, if you see 2 bursts with the same dispersion, you can be kind of sure that they are coming from the same object. But if the dispersion is completely different, there is no way to get enough material changing in the light of sign for those time scales, let's say.
Are there many events that could fit into the first hypothesis? I mean, you do not have...
No, those are the known repeating fast reverse. So those are the ones that are classified as the same object.
Right.
And then basically this was confirmed when we have the good precision, the ones that has been localized even to their second level. This seems to be completely confirmed that all those events come from the same place for a given FRB, so it's a repeating fast burst. But then the other ones, there is no way to explain it and associate it with the same object.
Right.
Because of both, like the separation in the sky and also the different material that actually it's required to be there.
Right. So they can really repeat. I mean,
yeah.
Okay. Okay. And this comes to my third question. The mechanisms, right? As far as I know, the best candidate, I don't know, you may tell me if I'm right or not. The best candidate would be magnetars, and these events could occur on the surface, in the cracks, by the cracks in the magnetars. And then in this case, you have something that is related to a massive compact object that could be either in a massive star-forming region or in a globular cluster, right? Regardless of metallicity, it doesn't matter. What matters is the plasma physics process on the surface, the crack, and that there are, I mean, the models that I saw are reliable in the sense that they can reproduce these spikes and the luminosity, etc. I'd like to know your comment on this, if this is really the preferred process or if there is a debate, a complete, there are other candidates as reliable as this physical process.
Yeah, so actually, yes. Again, magnetars are getting us the most promising because the galactic one and also all the emission can be naturally explained around a magnetar. Until now, and even still, for some FRBs probably, you had the two most promising ideas that they were giving similar results in most of the aspects. One was the magnetospheric emission, like the emission really comes from almost the surface of the magnetar.
Right.
And the other models were actually predicting that the emission doesn't come from there.
Yeah.
But basically you have the emission in the interaction at outer layers, like outside the light cylinder in case of pulsar, for example. That is basically interaction, and you have kind of a maser emission that is triggered by the supernova remnant. So something that is already, how you say, ionized, and then is where you actually can trigger that emission as a maser. It could be equivalent to one. Those two models were predicting more or less similar results, and both are consistent with most of the observations. Right. And they are something that supports one and the other. Like the problem with this magnetospheric emission is that you will likely get something more periodic, because at the end you have a magnetar that rotates on relatively short scales. So even if you can get that emission from different parts of the magnetosphere, likely you should have some periodicity there. Whereas the other emission don't have any periodicity, because at the end you are just getting a maser emission quite far from the magnetar. The problem, and that's why actually, yes, in the last year, the surface emission has been boosted, it's because of the narrowness of the bursts. Right. So when you go to microsecond, nanosecond emission, there is no way that you can do that on a maser type on basically a cloud next to it. It really needs to be from the magnetosphere of the magnetar.
The magnetosphere or the surface?
The surface, sorry, the surface.
Okay, so still the surface seems to be the
most promising one.
Promising candidate
right now.
Okay.
And then the only thing that is still a bit unclear is why in some of them you have this kind of periodic activity. Like in some of them you have a 16-day period, for example, when there is a window of 4 days where you have the activity. And then that window repeats every 16 days. In the other FRB, this window is about tens of days, and the period is around 150 days. So within this active period, there's no way to predict when the burst will happen, but you do have these active periods. So if it's linked to something that is actually intrinsic to the magnetosphere properties, or like in some cases, because still we can have different environments in different ones, is associated to some binary object. So on top of the magnetar and the surface, you have an orbit there that is actually affecting it.
Mm-hmm.
This is the part that is still to be completely understood.
Right. Mm-hmm. Okay, then. Thanks a lot. I really enjoyed to have this upgrade of this field. It was an excellent review. Thanks a lot.
Thank you. Yeah, it's the heart of these talks, because every month the results are kind of changing. So
okay, thanks.
Professor Reinaldo.
Benito, thanks for the very nice talk. The sources, this class of sources, I think they're very intriguing. I have a few very simple questions. About this event, you mentioned that it was localized near the globular cluster, the center of the globular cluster in NH1. Because you mentioned that in general, the fast radio bursts, they have a high degree, high dispersion measurement and also rotation measurement. For this event, it was also like this, with a high dispersion and high rotation measurement.
Yes, so this one in particular doesn't have a significant rotation measure, for example. And this is something that we see in most of FRBs, like most of them are really highly polarized. So the emission is near 100% or fully 100% polarized. That is actually not that common in different events. Rotation measure, we get completely different results. Some FRBs are like getting a rotation measure that high, like 10 to 5, like the first FRB that I explained. Other ones don't have any rotation measure at all, so it also indicates that the environment is less extreme in that sense. And other ones have some intermediate values. Concerning the dispersion, this one, yeah, like all of them are significantly larger than what you will expect from our galaxy. Actually, in this one, again, you assume a reasonable density for the intergalactic medium, and then you can get the estimated redshift or the estimated distance to the event. And actually, that's what it was used here to think that it was probably associated with the M81 complex, because the dispersion derived for standard intergalactic densities, plus subtracting the one from the Milky Way, it was consistent with the distance of M81. Like in that direction, actually, there are another galaxy, actually the one that I saw here. This galaxy here is just a background galaxy. It's much farther than M81. And this dispersion actually was used to also try to determine if this galaxy could be the host. But this galaxy is already quite far, and then the dispersion that you will expect, it will be much higher than the one that we observe in the bursts. So it's higher to be in the Milky Way. It's consistent with the...
It's nothing anomaly. Thank you. I was going to ask about the polarization degree, but you already answered. It's nearly 100% in the events, right? And I have one.
And some of them are circular, and some others are linear. Like we actually have a quite variety of them. So not all of them are 100% linearly polarized. Some of them also exhibit some circular polarization. And they are typically really highly polarized, most of them.
And I have one curiosity, because this flux is not so low, right? So I wonder why, my curiosity, why it was only discovered in 2007. It's something related to the transient nature, that the instruments were, I don't know, not so have a sensitivity for quick transients. Why is it so? It was only discovered a few years ago.
That's a very good question, actually. Actually, more important, or actually what explains partly that question, is that it was discovered, the first one, it was discovered not in new observations, but just reanalyzing archival data from parks. So the problem is that we have radio observations, and oops, can you hear me? Oh yeah, okay, it's fixed.
Yes.
We had the radio, yeah, okay, because I froze my video. We had radio observations and in other wavelength ranges. If we go to the millisecond time scales, we knew pulsars from the 70s. And as I mentioned, the pulsar produces a very deterministic emission, like it's completely periodic. So actually, everyone, the only thing that you knew on those time scales are pulsars. You know that they are periodic. And the way that you have to improve your sensitivity is to combine data, of course, and fold with the period of the pulsar. So all the searches that were conducted until 2 decades ago in radio observations were folding data. So all the searches are optimized to get a radio observation, fold the data to search for periodic emission on these scales. The problem with fast zero bursts is that they don't repeat. So in one observation, you may have only one burst, and that one will, even if it's really bright, completely saturated your instrument, it will be filtered out because it does not, it's not periodic. And that was the main problem. Like, we had the sensitivity, we had the observations. Likely, many of them were already discovered, detected or recorded in the instruments. But we were not conducting any search.
Right, we were not looking for
it. Yeah.
Yes, very interesting.
And it was only when they started searching for single events when they started detecting these events. And the last one is the dispersion. Like, the tail here is completely unexpected because they are much farther. So for any object in our galaxy, the delay in the time is just a few milliseconds. It's not even more than 100 milliseconds. So all the searches were optimized to what you know, of course, as happens many times. It was searching only for delays of few milliseconds. If you see something that was covering a 1 second range, then you will filter it out thinking that this interference or anything.
Right.
So that's basically the explanation of why
Thank
it
you.
was so late.
It's really interesting. Is it easy to deal with the catalog of the FRBs? Is there a catalog easy to use?
Now it's getting, now we changed to the transient catalog, the transient survey. So the thing is that it has been changing because, yeah, at the beginning you only have a few, then suddenly in 2 years you got hundreds. There was first a catalog, but now it's getting into the transient TNS. I forgot about the acronym. The transient survey, basically the database there. And now it's yeah, easier to go through it and keep up to date all the properties of the fast zero burst. But it is something that, yeah, is still happening. Like, even name conventions happened last year because the first conventions were proven to not be that much useful with the new numbers that you get. Yeah.
Thank you very much.
Well, thank you again, Benito. I think we can end the transmission on YouTube, but for anyone who wants, we can stay here in Google Meet. Richard?
Yeah.
Thank you again, Benito, for your time, for the presentation, for sharing your knowledge on the subject.
No, thanks for the invitation.
I appreciate it a lot.
Talk there, so.
Yes, thank you. It's very,
Yeah,
very interesting.
I found it really interesting. And I knew nothing before your seminar, almost nothing, but now I think I know a lot more.
Yeah, and it's getting more.
Yeah, I try to keep everything, all the context at least. So. because
yes,
again, it's a bit far field for.
Yes, something I would like to learn more because I really got interested. It's
Yes.
no problem.
No.
This will be record on YouTube.
Yeah. Well, thanks, Marisa, Maria, and everyone for inviting me. It has been a pleasure to think, and I hope that everyone join the seminar.